Hello, everybody. So, all of you can see the slide?
Yes, sir.
Okay. Good evening, all. And thank you for having me in the second day. And I hope all of you had good learning from the yesterday presentation. And we will have a new presentation today, which is secure cyber physical systems by design. Okay, so we'll have as yesterday, but like around 100 slides, okay, which I will glance through. We'll and after the end of the presentation, we can have question answer sessions. Okay, so what this is a very interesting idea that you learned today, where what is the topic as per the topic, what it suggests, that is you might have heard already the IoT and then followed by cyber physical system. These are two concepts which are interrelated, and they may be even same, both IoT and CPS. Okay, but there are some commonality, some differences. CPS in general is a bigger umbrella, okay, than the IoT. Okay, and we'll have some discussions on those directions. But the idea here is how to secure CPS by design. Okay, so that means we are basically planning to secure the cyber physical system by going to the basics of the CPS. Okay, instead of having a CPS and then retrofit security features. So that's the big idea. Okay, which is called security by design or secure by design is a new concept that is evolving, where security features will be added to the CPS right from the design phase. So outline of talk is like this. We'll have CPS as a component of smart city. We'll discuss what are the security challenges of CPS, what are the drawbacks of existing security solutions, what is that we call as a secure by design or security by design, which is also what is called hardware assisted security as a subset, and we'll have some conclusions and so on. This is the big picture we'll discuss as a smart city. Smart city, including many of you are from Bhubaneswar, that is that has a plan to become a smart city eventually, and a lot of projects are being undertaken as government of India and government of Odisha are promoting. And here the concept of smart city essentially came from the fact that we have limited resource, maybe natural, maybe man-made. Okay, and that limited resource we need to use effectively so that the cities can sustain. Okay, and what is predicted that is by 2050, 70% of world population will be urban. So that's a serious organ, what you can say, urban migration, population migration to urban, and so no city can sustain. Okay, and it's essentially around we're talking about 20-30 years down the line, we'll have a serious population explosion in the urban area, and so it's the right thing to take this as a serious matter, and we have something in place so that cities sustain. Okay, and because a lot of people have now started seeing that smart cities concept can be a successful concept, so different related things are evolving now. For example, smart village, which again government of India has started. Okay, which like again a lot of political motivation is there, and there is technology existing. IEEE, what is very good thing is IEEE is promoting these things quite a bit, and IEEE has a lot of activities in India related to this smart city, smart village, and so on. And in the long run, smart city, smart country can be done, and Singapore in itself is a smart country in that sense. So, what technological standpoint, smart cities come from three different I's that I call. One is instrumentation, second is interconnection, third is intelligence. Okay, instrumentation essentially some type of sensing and actuation. Interconnection is the connectivity of the sensors, the things. Okay, and Then intelligence, that is the data that we gather in this process of instrumentation and interconnection. With the data, how do we retrieve information and then make right decisions for the city? For example, let us say which area of the city needs to grow, which area of the city potentially can be flooded, okay, which area of city has even health situations, okay, all these things are intelligent decisions, okay, which can come from the data, and that is coming from various types of sensors and their connectivity helping to gather the data. Now, if we see the big picture of Internet of Things, which as we now know, the three I's, that is the instrumentation, the interconnection, and intelligence, the three I's are essentially coming from IoT. So it's a good idea, that's why, to have some what you can say concept of what is then IoT. So IoT is a collection of sensors with connectivity. Okay, so we have different things which are sensor, actuator, microcontroller, all these things, and then they are local network, which can be LAN to start with, or it can be more specialized kind of scenario where it's called body area network for the Internet of medical things, or it can be a control area network CAN for the smart vehicles and so on. And cloud is always there to do something or other, that is at least to store the data and to do bigger analytics and so on. So then we can conceptualize IoT as a configurable dynamic global network of networks. Okay, and those who are from system background, we can consider this as a system of system. So that's the big picture of IoT. And yesterday we discussed this fact that is a specific instance of IoT is Internet of Medical Things, which is IoT in the healthcare domain. Okay, so this has specialized sensors, which are body sensor, and again a specialized connection like a body area network connection and so on. And then data aggregation is happening, and the data analytics is happening, and the long-term data storage in the IoT cloud or IoMT cloud in this specific case is as in the form of electronic health records, which is basically large volume of data and stays in the IoMT cloud. And so IoMT, that means we discussed as a specific case of IoT in general, what we have. Then other type of IoT, which is these are much bigger industrial application kind of IoT, is the industrial Internet of Things. Okay, and right now much more demand is there for industrial automation, and even what they call additive manufacturing, one concept is that is evolving, and then even how to have effective management of human capital in the context of the big industries and so on. So all these are basically possible by doing something more intelligent and specific IoT that is what you can say effective in this situation is industrial Internet of Things or IIoT. So these are two different examples, and many more we can think of, which are a specific type of IoT. Now, if we correlate these three situations, okay, we have Internet of Things, which are basically different sensor actuator, their connectivity, and then when deployed in the case of physical entity like transportation, like energy, okay, then other big infrastructure and so on, like factories. So, okay, so they make CPS. Okay, so IoT plus physical entity in that respect, we can say together become CPS. And a set of those CPS make smart cities possible. Okay, we can have transportation CPS, healthcare CPS, energy CPS, all these together make smart cities. So if we simplistically think that what is that smart cyber physical system is that is making smart cities, cyber physical system is very close related three different entities. One is cyber, second is physical, third is system. Okay, and they are doing what we call as three C's, that is computation, control, and communication. So similarly, one can comprehend the IoT as connect, compute, and communicate. So in this essence, if we see that is there are a lot of commonalities, okay, but in the previous slide, the way I conceptualized, IoT is a smaller domain that makes a biggest CPS, which is bigger domain, and then a set of CPS make a smart city. Now, healthcare cyber physical system is a specific example that we had looked at yesterday, and yeah, so we can comprehend this situation here. IOMT is underneath technology, and when IOMT is deployed in smart hospitals, then smart homes, then in the like in smart cities and so on altogether. Okay, that component of IoT with physical entities is giving us what is called healthcare cyber physical system, or HCPS. Similarly, we can comprehend this situation, which is energy cyber physical system. So energy cyber physical system makes the existing energy sector, for example, the transmission, generation, transmission, distribution, whatever is existing, along with that integration of industrial IoT in this case makes what is called energy cyber physical system. And as a result, the way healthcare we saw, that is, we have more personalized and effective healthcare management where user is a participant and getting more one-to-one kind of attention from the author, from the doctor. Similarly, here, more effective power transmission, generation, transmission, distribution can happen, and the customer even can give back to the grid, okay, and get energy as well. Now, if we see, this is a related slide of energy CPS, where what we see here, that is Internet of Things making energy CPS possible, and a specific instance here we can consider as Internet of Energy. And here, previous slide, we saw a bigger scale where we come from the generation unit to transmission, then distribution. Then when we see this in a little bit more detail, where home is coming to the picture, what we see here, let us say smart grid and smart generation is there. Then storage, how we can do better, whether, for example, we can use supercapacitors like mechanism to store that can come under this, and we are all using harvesting and so on for the energy that is there. But most importantly, in the middle, what we have there in slide number 13 is smart consumption. Okay, so smart power consumption, because electricity is something, okay, people can say yes, we can store it, but is much more direct relation between consumption and generation. If we even though we are storing battery, okay, very small percentage of energy that is generated actually stored in battery. So energy consumption demands generation. That's why how we smartly consume. Okay, for example, when we are not at home, do not switch on the air conditioning unit. When possible, maybe switch off the refrigerator, which takes a lot of energy. So anyway, so like that, we can control the consumption. Okay, that is the key thing. And so we do now, I mean, this is a feasible technology. We all have at home like smart energy, where that system, when we are not at home, is taking care of air conditioning unit, and all these appliances are now much more energy efficient and so on. So this is smart energy. So what we saw in this set of a dozen slides is Internet of Things, cyber physical system, and specific instances of cyber physical system. And there are much more. I haven't included here agriculture cyber physical system, for example, which is a big deal. Okay, and all these things are there. And a collection of CPS is making smart cities, we saw. Now, the next set of slides, I mean slide number 14, what we'll discuss is security challenges in cyber physical system. So what are the vulnerability and so on in cyber physical systems or CPS? We are aware of this big picture. We hear this news like that is this system is hacked, Yahoo is hacked, and ransomware. Okay, all these we hear all the time. Okay, these are cyber attacks. Okay, and what they achieve in this process is to get access to a lot of data, personal information, credit card information, and so on. Okay, they get access. And in the middle, what I call them that I have written is these are actually IT security issues. Okay, information technology security issues, and these have their own consequences. Okay, and objective here for the hacker is to create a chaotic situation and make some money out of it. That's the objective here. Okay, and then what I consider as a much more serious problem is here, slide number 16, which is security challenges of systems. Okay, the previous one I showed you, that is IoT security challenge. Okay, but this is IoT security challenge or CPS security challenge. This is a much bigger scale that can happen. At the same time, smaller scale also can happen. But what is more important compared to the previous, what I call as IT security problem, this is IoT security or CPS security. These are much more, what you can say, life-threatening situation. For example, in the smart or autonomous car, suppose a autonomous car or a driverless car is hacked, then that driverless car may have accidents, which is having more direct personal injury and life-threatening situation. Then power grid attack is real, is much more serious. And the left side diagram, I have an example where Ukraine power grid was hacked. Okay, and that can completely make chaos of the whole city. And I imagine a cyber criminal is taking control of the smart grid, and then whole in the, let's say in the evening we are sitting at home, and a cyber criminal has access to the smart grid of the city or of the nation and completely power shut down. Okay, so those are much more serious consequences than getting credit card information and so on, and they are much more difficult to solve. Okay, and in the right side I have a UAV drone. That is again a reality where drones can be hacked, and drones are now getting a lot more attention because of their uses in not just military application, which has been there for last several years, okay, but now more civilian application. For example, I see in US, like in where the agriculture belts are there, so a lot of drones are used for the aerial survey of the large farming lands. Okay, that is an application. Another application is, for example, all these retailers like Amazon and so on. What they are trying to do, they are trying to have drone, and that's again not a scientific fancy thing. It's a reality. Okay, and the drones will deliver different items to the doorstep. So imagine hacking those. So those have more direct consequences to human life and are serious problems. So from these two slides, what is the conclusion is IT security we always have, and we will be continue having. They have their own set of difficulties, but IoT or CPS security are much more serious, and we have that can cause rather personal issues that affects directly, and we have to worry about those. And these are more difficult that we will see. Now, much more closely, if we see a personal level, okay, we have like imagine the pacemaker being hacked, or a smart cloth or a wearable is being hacked, okay, and then drone and then transportation device, all these can be hacked, and if not at all, if not hacked, at least there can be privacy violation in these in different contexts. So all these are serious security and privacy issues. Now, when we see the three different words, what is called security, privacy, and intellectual property rights, they are related, but they are not same. They are consequences of those vulnerability can be different levels. So, security aspect, one can worry about system security, data security, and then they are related, they can be related as well, okay, but they are not same. And then similarly, system privacy, data privacy can be there as problems. And then intellectual property rights, okay, that is like data ownership and hardware ownership, all these are also different kind of security problem. So they are related, but they are not same. But in a big picture, everybody refers them as security threat, but they are not same. Now, when we see a simple embedded system, for example, like a smartphone or a media player and so on, okay, we have different things here like a DSP, okay, embedded processors, memory, operating system, and application. So if you look at it closely, what are the security vulnerability, then we can find out there are several, okay, a lot of them are there. And so that means when we are having a mobile phone in our hand, okay, engineers, scientists have taken care of these. That's why we are having that phone. But many of them have been solved, okay, but many of them can be always updated. More and more serious security threats can come, and that's why research is always ongoing. So we can see in this context, so that is physical attacks can happen, memory attacks can happen, firmware can be attacked, and everybody is aware of password kind of problem, that is because of network security, OS security. But in addition, like IP attacks of the hardware, then copyright attack of the information that is being processed are there. And all these are problems and need to be solved. Now, an example of a privacy kind of attack, this example is a system privacy attack. So a lot more things are there, but a simplistic understanding is a system privacy. It tells details of the privacy, details of the system. Okay, that is the configuration of the system. For example, what you have inside your car. Okay, and those details can help later on a hacker to break to your system. So privacy eventually can lead to security problems. Then these are personal privacy problems where basically personal data is being compromised, okay, and then as a result, later on, this can be used in wrong purposes. Now, security point of view, when we want to consider specific examples, like for example, medical, which we had extensively talked in the yesterday discussion. So security to the medical devices, which is essentially part of system security, we can say, or a device security, okay, can be in many ways: eavesdropping attack, impersonate attack, reverse engineering, and radio attack. All these things can be there, and we can solve those using various methods, and we'll be discussing some today. Now, CPS point of view, if we want to see the attack on the smart grid, okay, and smart grid vulnerability can come from many sources, and this figure illustrates that, that is attacks can come essentially wherever there is a software kind of mechanism and a microcontroller kind of mechanism. Okay, so like a SCADA system in smart grid can be attacked. Okay, then PLCs and so on as a what you can say as a microcontroller and other point of view, they can be attacked as a device and as a system overall. So these are smart grid vulnerability, and this is real. This is a much more serious problem. For example, this slide 29 here I have that shows what are the vulnerability and how the threats come and what is the impact. So the first one shows Ukraine power grid attack 2015, then Alabama Brown Ferry plant attack in 2006, okay, and in South Korea 2015. So these are real and these are much more serious, okay. And then one nuclear power plant had to shut down in 2008, okay, emergency shutdown. So you can see those are very serious, and attacks come from various sources, okay, and various bombs, and we need to solve those. Now, talking about transportation, okay, we have autonomous car. Autonomous cars have a lot of electronics, a lot of softwares, okay, and hundreds of electronic control units and 100 millions of lines codes come from different vendors for different components of the car, and they can have massive security issues, okay, and a lot more details are there, but that's the big picture things, and we need to solve those, and this can be, unless you solve, this can have serious problems. Now, this is the most scary in the autonomous vehicle I find, okay, that is in the previous slide, you saw different electronic control unit and their software are vulnerable, okay. Then the most scary thing that I find, that is the signal when it goes after taking certain decisions in a car. Continuously, we are getting a lot of data from the sensors. We have the models, machine learning model, okay, AI models, and those are making decisions. And then that decision is conveyed to the actuator to take certain actions. For example, if a decision is to put a brake, actuator should work and put a brake automatically. Now, if some reason the sensor signal is not going properly to the actuator signal, somebody hacks it and so on, then autonomous car may be interested to put a brake, but it instead speeds up, or it in suppose autonomous car wants to take a left turn, but it instead takes a right turn. Those are the situations that one is to worry, and those are much more serious than any other hacking that I can see. Now, in terms of security situations, okay, NFC are also important component. That NFC are small components in bigger CPS. Okay, that is whether we are using cashless payment or we are marking attendance or physical access. All these things can be done through NFC mechanism, and that it can be hacked in various ways. And we need to have some mechanism that controls those secret problems here. RFID is also it's a small thing again, but it is a part of much bigger entities that is used for access control, that is used for payment processing, and so on. So all these numerous applications it can have in the CPS, and it can be attacked or hacked in so many different ways. And from RFID threat to RFID channel threat, physical threat to channel threat, all these are possible, and we have to solve. Now, this is a very simple example of what we can call as Trojan. Trojans are different problems, and actually this is again a much more difficult attack to handle. Okay, so Trojan essentially is some sort of modification to the designs of the system or to hardware, so that modification can be used to have backdoor access. That's the big idea of the problem. And those Trojans then can cause serious system vulnerability. Now, another very interesting discussion here is we are solving most of the security problem by using some sort of encryption. Okay, that has been the norm. And if you see AES encryption, what was the prediction when the AES came? 128-bit key, if we want to hack by brute force method, may take billions of years. Okay, which is when it came, that was the prediction. Okay, but that's not the case. Okay, now we are using even 1,000-bit key, but can be hacked. For example, recently it has been demonstrated that a quantum computer is able to hack a 1,000-bit key in a few hours. Okay, so it's a much serious problem. So even without using quantum computer, okay, these are hardware-based methods that can hack the security systems. Okay, side channel attack. Okay, so various forms of side channel attacks are there, and these side channel attacks basically do not try to defeat the cryptography. Okay, to go to brute force and so on. They do not. Rather, they do power analysis and other mechanisms. Okay, to guess the key, and which works, and anything in this mechanism can be hacked in matter of hours. Okay, and another kind of security problem is firmware, breaking of the firmware. And firmwares are part of any embedded system. Embedded system are part of bigger things. So that is why this is serious consequences for any type of CPS that we deal with. Okay, and we need to worry. So whether the embedded system goes to power area CPS, powers any CPS, or goes to agriculture CPS anywhere, there is firmware, and we need to worry about the firmware attack as well. Now, memory is a serious issue, memory problem. Why? Because memory are part of everything. We store, we compute, okay, and that as a result, we have memory as a very important component of any system. So it can be attacked in various ways: snooping, spoofing, and replay attack. All these are possible. So now we are trying to make everything intelligent or smart, we call it. Okay, and AI at the same time, the AI system that we are using or AI models that we are using can be attacked as well. So AI security is a serious problem, and it can be attacked in many ways. Okay, and during model testing, model preparation, and so on. And even during model training, if you have bad data, okay, then we can have different results, different AI models, and can be have different consequences. Now, here is an example how AI security can look like. For example, let us say autonomous vehicle, okay, and there is a stop sign. And if that stop sign during a model is wrongly labeled as a speed limit sign, then there is a problem. Okay, and the right side clearly tells an example instead of stop. If it shows the speed limit as a then it can have serious problems as we see here. So we have been working, right? These are slides that tells what are the security scenarios in different cyber physical systems. And we have been working, a lot of researchers around the globe, of course, are working to solve these issues. And we'll see what are the problems, okay, of the existing solutions. Now, so here, like CPS security wise, if we see there is it's multi-form security problem, confidential problem, integrity problem, availability problem, authentication, non-repudiation, identity, and location privacy. All these are different issues, and there are certain solutions. Okay, current and mostly you can see are based on cryptography. They have certain advantages, they have certain disadvantages. And in the interest of time, I'll show those problems are there. Now, when I categorize, and we can say that many are handled as a problem of IT security point of view. But when I compare that IT security versus IoT security, what I find here are is listed in slide 51. So IT security basically are well understood, and they basically are being used, okay, but they have their own set of limitation in the sense that is they are specifically geared that is there is a lot of computational power, and then we can use heavy duty encryption kind of solution to protect. That's the that has been the underlying principle, that is use encryption as long with the longest possible key, okay, 1000-bit encryption and those kind of stuff. And we have accessibility to different computational power, and that fixes the problem. That is how it has been. But when we talk in terms of IoT security, okay, then things look different. Okay, a lot more devices. Okay, instead of IT, which is million, these are billions of IoT devices. And what is more difficult problem, that is it may not be having any computational power. Okay, so in a sensor, okay, there is no computational power, very minimal computational power compared to a server in the left side, which has a lot of computational power. Similarly, IT security in the left side can be costly, no doubt, but IoT security in the right side can be life-threatening. So those are different scenarios, and we cannot use IT security to IoT or CPS security straight away. Now, if we see a specific example, okay, that is, for example, let us take a pacemaker or neurotransmitter. These are implantable hardwares, okay, and small, tiny hardware. And pacemaker battery life is 10 years. Neurotransmitter battery life is 8 years. So if we put encryption at the top of it, first of all, they may not execute because they do not have computational power. And at the same time, if at all they execute, they will drain the battery. Okay, and replacing a battery needs risky surgical procedures. So that is the level of difficulty we are talking about. Okay, things are very difficult in IoT or CPS domain. See the situation. Okay, smart IC security. So what we can agree from the healthcare, that is energy security. Medical security is energy constant. Okay, they have computational as well as battery life problems. Now, if we go to the smart car or smart transportation domain, which have security vulnerability, there we can see here that is they can have latency issues. We need to, any security solution that we need to put in a car need to work very fast. Okay, that is in the time of order of magnitude milliseconds. Then only they will work. Otherwise, they are ineffective. So this is a latency constant problem. Now, when I go to drone, which are much more faster running, they are battery driven, but they have range limitation as a result of the battery. So battery is essentially determining the range of the drone devices. So we can say any security that we add here has to work fast, has to be way less burden as possible to the battery life. Okay, and to the, we do not want a security solution to become an additional payload to it, essentially, simplistically speaking. And so here is a much more serious problem where energy and latency constant both can be problematic. In the power area, similarly, like if we want smart grid security, okay, we have to make sure that it doesn't take more time to work. Okay, it's a latency problem because power is again a real-time scenario, and then as less overhead as possible in terms of latency, then the performance of the embedded system that is doing all these that is part of any of the smart grids and so on. So so all these problems are there. Then another thing I wanted to bring to your attention, that is blockchain. We had some discussion yesterday, and blockchain has a lot of issues. Okay, starting from high energy consumption to lack of storage capability, and 51% attack is a much serious problem, and it has been demonstrated. In last year, I think Bitcoin was hacked at least 2 times with the help of 51% attack. And all these have challenges, but still people explore to use blockchain for various applications. That is why we need to look at it. What are the secret vulnerability? And energy is a primary problem of blockchain so as of now. And I compare here, that is energy consumption of each Bitcoin is Bitcoin transaction is 80,000 more times than a transaction of a credit card, and mining a Bitcoin is serious energy problem. Okay, the energy consumption of a 2-year US household is equivalent to the Bitcoin mining. So it's a lot of money to mine a Bitcoin because energy consumption is too high. Now, if we see the security of blockchain, okay, then it has a lot of problems. 51% attack, then identity theft attack, all these are possible. Okay, and we need to fix, and there are solutions people are exploring, of course. But in addition to the security, blockchains have privacy issues. Okay, I have highlighted some. Okay, that is blockchain do keep track of IP address. Okay, so Bitcoin, Dash, then money, all these different currencies, cryptocurrencies, and all these keep track, and that's a privacy issue as well. So here, one side people are talking about to use blockchain for security. Then other side, what we see that is blockchain has a lot of security privacy issues. A specific example of blockchain is the smart contract thing. Okay, and smart contract has a lot of vulnerability that ether lost, then immutable bug, and all these problems are there. And still it's working reasonably, but all these security vulnerability, smart contract, which is a specific example of a blockchain is there, and many more different. Of course, the implementation there. This is one more widely used, and I thought of bringing to your attention. Now, if we analyze, we in the like a few minutes ago, we analyzed IT security versus IoT security, and this slide, what I'm trying to show is a software-based security attack versus hardware-based attack. Okay, so security attack, mostly people are familiar, are software-based attack, which are remote, which are more frequent, and happening through the communication channels. Okay, and DOS attack and other things we are aware of. Okay, are examples. Then hardware based, the physical attacks may be local. Okay, and what is important here, those are very difficult to prevent because they're happening because you bought a bad hardware. Okay, for example, you bought a bad hardware that you put in your autonomous car, you put a bad hardware in your mobile phone and so on. So those are serious, local, and you have it even without knowing or with your knowledge. Okay, you have a security crisis there, and those are much more difficult to solve. Okay, as a result. So now, when we want to solve these security problems, so we can do software-based, we can do hardware-based. Software-based introduce latency because it takes some time for the encryption engine to work. Okay, then it needs some level of computational power. It cannot do on its own the computation. So on the other hand, hardware possible to do high-speed operations. Okay, and it can be basically used in the form of ASIC, in the form of FPGA. So as a result, it can be low cost, but you cannot upgrade hardware. That is its problem. But positive side is we can integrate in the system. Okay, so that is the positive side. And more hardware-based system can be more geared towards IoT, whereas software-based solution can be more geared towards the IT. So that's the difference that we see. So we have now with these slides understanding of IT security versus IoT security, software-based attack versus hardware-based attack, software-based security solutions versus hardware-based security solution. Now, in general, when we are trying to solve the security problem of IoT or CPS, so this always comes to a picture, it becomes a multi-dimensional optimization axis, okay, or a space, okay, and with the different axes like energy, security, then the smartness or intelligence aspects and cost. So these are different multi-dimensional optimization space that one needs to deal with. How do you then handle this this multi-dimensional optimization space is a problem, and to handle that we will be devising the solution later on that I will come to. But here is a very interesting slide, okay, that is all the security things we are talking about, okay, will have a serious consequences later on, okay, in the form of security, so basically mechanisms being hacked, where we are essentially doing guessing of the key, okay, much more easily with the help of quantum computing and so on. So quantum computing eventually, when it becomes mainstream, can be a security nightmare where 1,000-bit encryptions are being hacked in certain hours. Now, to basically have this design space that is multidimensional, we have to have certain solutions. So what we discussed here in up to slide 69, we are in now in slide 70, up to slide 69, what we discussed is what are the different types of attacks that is possible in the CPS or IoT space, and as a result, now we are needing a solution which is multidimensional that solves the problem of security without putting a lot of energy overhead and without putting any overhead on the latency. Okay, and what paradigm that we are discussing in from slide number 70 is what is called hardware assisted security or secure by design. So just a little bit background, okay, that is hardware assisted security is a mechanism that I've been using for last, I would say, 12 years or so. So where I first time coined this term when I was doing watermarking, and I called hardware-based, hardware assisted watermarking. So the idea there is that is how to have watermarking processors so that doesn't become overhead for the host electronics unit. That is the idea. And then now the way people have been accepting those kind of facts, and secure by design or security by design, they use interchangeably, that as coined. And so I consider HAS is a hardware assisted security is really a subset of the security by design, and we'll be discussing that in few slides left in this discussion. Now, to give you again further background, privacy by design, okay, came in, I would say, mid-90s, okay, 1995, okay, and that then after a long time, as you can see, more than 20 years, that became a law in Europe's General Data Protection Regulation. In that, it became part of it 2018, okay, and then People have then started thinking, and then it is coming now a bigger umbrella, okay, that is security by design or secure by design, SBD. So that's the background. Okay, so three things here I'm talking about. One is hardware assisted security we talked, then privacy by design, then security by design. So security by design is a bigger umbrella that is encompassing everything, but European law has so far privacy by design. Anyway, and actually it reminds me also like Millennium Digital Act when it came in 2000, that covered only the watermarking portion, which is basically copyright aspects. Okay, anyway, so now what is the essence of security by design is this, that is embedding security features, okay, in the form of hardware software in the various products, program and services. That is the idea. Okay, and why? Because so it's embed, that means you go to the drawing board, go to the basics of design and do things there. Okay, and why we're doing, because retrofitting, that means adding features after the design, is much more difficult. That's the point. So there are different what you can say 7 principles that originally was coined. Okay, that is to have security or privacy as a proactive, not reactive. And then it should be a default, it should be embedded in the design, and it should be what is that as a fully functionality, that means it should not be overhead. Okay, and it should completely protect the life cycle, and then at the same time it should respect the user. So that is the what you can say 7 principles. So hardware assisted security essentially is a mechanism that provides security to the system, to the information, and to the hardware itself. Okay, and we can consider this as a part of secure by design or security by design, and we can achieve that by adding additional hardware component, and we can achieve that by doing design modification to the hardware, to the systems. Now, these are a few things that is basically in there, and we can consider that as essentially with this philosophy of cyber physical system security as a security by design. Okay, hardware security module, HSM, are part of different servers and so on. Trusted platform or TPM are part of many computer hardwares, and trust zone is coming to the different ARM-based systems, mobile device, and so on. And in the bottom, in the slide number 78, I have in the bottom right what is called physical unclonable function, which is there as a part of security primitive for many embedded systems. What is the physical unclonable function? Okay, these are primitives of security that can generate different numbers. Okay, which can be which can be used for security later on, and that is the unique aspect is there is a very unique input-output pair. Okay, which is called challenge and response pair. Okay, and this number response, essentially this number is generated on the fly for the security and is not stored anywhere. That's the big deal. So response can only be obtained if challenge is existing and the POF is existing, the hardware primitive is existing. So the key idea, POPs do not store key, they generate key on the fly. Okay, and that's why the POP is essentially needed, okay, to get that key. It's like a key, you can say for a door, okay, you have a specific lock, and that lock opens in specific key, not using anything else. We can visualize that way. Now we designed a lot of variety of POPs, and these are some examples. So we designed power efficient POPs, then POPs which runs at high speed, okay, for various application, for health domain, transportation domain, and so on. This concept I gave a long time ago. That is, I started working in end of my PhD time. Okay, and this is a single author paper I published in 2009. What the idea here is to go to the drawing board of the camera design, for example, as an example I took. Okay, and then add different hardware features, and then do the optimization of the overall design such that addition of those hardware features do not compromise the battery life and so on. Okay, so that is excellent design. A lot of people have liked it, and it has been widely adopted by many people for future research in this direction. And this here is an example of how we are going back to the drawing board of healthcare CPS, and then adding, for example, POF in different components, for example, at the end device, at the edge devices, and then giving different protocols so that users can use it for security purposes. PMSec is what we did. And we developed for that different security protocols for when a new device is bought, what doctors has to do, and so that the doctor can later on verify the device, what you can say, identity, and then reconfigure and do some things later on when doctor needs to do it. So we developed a complete protocol with using physical on-clonal function. And what is key idea in the previous slide here, that is POF, its security is foolproof, because the device will get access only if the POF that is with the user and POF with the server, that is doctor, they are in place. Then only the what you can say security can be what you can say security then is foolproof as a result of that, because those two POPs are essentially together as a combination working to allow each other access. That's the important point. And the keys are not stored anywhere, so key somebody cannot use to compromise the security mechanism. Then when that same doctor, which is authentic user, okay, wants to have access, then doctor can have access by following this mechanism. And what is the key part here? That is POF of the doctor, POF of the device. That pair, okay, if they are here pair present at the enrollment phase or at the registration phase, that means when device was first time put, then only that can be basically used to do the authentication. We have completely developed the system with its interface and so on, because we know like doctors and common user may not be tech savvy, right? So we have to have a simple mechanism. So we have a simple interface, and that basically tells the doctor, yes, authentication, enrollment is done or authentication done, we develop. And we verified completely the design, okay, and with the dummy devices and so on. And this is simple microcontroller. This is a simple Raspberry Pi like mechanism, and these are doing like excellent security with a very minimal power consumption in the range of 200 watt, and verifying the security in less than a second. Now, this is our big vision that I'm working in the context of I was mentioning yesterday, that is diabetes pro point of view. We want to have a foolproof system that is monitoring the glucose level non-invasive fashion, and at the same time injecting some level of insulin in a secure fashion, so that doctor can do administration of some level of insulin when needed, or configure the machine. Okay, and then at the same time, it needs to be ensured that a hacker cannot get access to the insulin pump. So we are developing system, and we have some solution now where we did a POF based. We integrated a POF in the glucometer, iGlu we have, and we have a foolproof 256-bit security. Okay, and user has choice to use any of these bits, 64-bit, 128-bit, and so on, and to ensure that the insulin pump is getting commands for insulin secretion at a right dosage level that is needed, not by a hacker. Then here is firmware is very important. I have mentioned, okay, that is firmware part of any electronic system that we are using in the CPS or IoT or CPS, and firmware security that's why it has to be handled, particularly in the case of car and so on. And we can basically what you can say use a POF in this case as well. Then smart vehicles or vehicle security is important, okay, because of various reasons we have discussed. And here is one solution I wanted to bring to attention. That is, and this is actually much more difficult problem. The reason being, this is the latency. Okay, we need to have decisions very fast in the smart and autonomous vehicles. So people have been working, and this is one example that watermarking, dynamic watermarking has been used for collision avoidance. Okay, and in this right side figure that has some built-in POP security in the autonomous cars, where the CAN bus, that is the control area network, which is the local area network of the cars, of the autonomous cars. Okay, and they are being protected by using POP, and where we have some results here that will come later on as a very good work in a journal paper. We will have foolproof solution for this. And blockchain, yesterday we had some questions, very interesting questions, very interesting discussions, and I'm discussing that blockchain aspects a little bit more. That is blockchain being explored as a use in many different cases, particularly CPS. Blockchain was not meant to be done for that, was not meant to be applied to those application domains, but people are doing. So we thought of that's why revisiting blockchain, and again our philosophy, as you can see, security by design. That means we are going to the drawing board, we are going to the basics of design and revisiting those designs to add secret features. So we did the same thing for the blockchain here. So our target here is to run the blockchain not on the server, but at these devices or even end devices. Okay, that is something like a Raspberry kind of thing, or in a phone and other things. So we that's why we came up with a new consensus algorithm, what we called as proof of authentication. Okay, and for proof authentication chain is the chain blockchain that we have developed that takes care of a lot of security things. And these are the, when we then compare where we stand with respect to other consensus algorithm. Okay, a lot of consensus algorithms are actually validation based. For example, proof of work, proof of stake, and so on. And then like other things are coming, like Ripple, proof of vote, all these things are voting based. Then we are developing new generation thing, what we call as proof authentication, that is authentication based. So that means we are using either a cryptography mechanism or a POF to do authentication. Okay, and we have very good results that you will see. So we first went back to the drawing board, as I said. Okay, we then figure out where are the actual what you can say problems, okay, of the blockchain. We find here that is block validation is a problem, transaction validation problem, and here there are a lot of energy that is because of proof of work, like serious heavy duty mechanisms which take a lot of energy, and all these places we need to transaction block validation. Okay, all these places we can go back and revisit the encryption and other things used. So we came up with one idea called proof authentication as compared to proof of work. Proof of work, we are in slide number 102. Okay, in the top we have proof of work, where solving a puzzle, which is a cryptographic puzzle, which is on energy hungry, computational resource hungry. That we took that out and we replaced that with authentication mechanism, cryptographic authentication mechanism. So we have a new consensus algorithm, and that is we call that as proof authentication, that is doing the authentication of the blocks. So we have to go back to the basic, and we redesigned the block structures. Okay, we have a block of a previous, then we have hash of previous, and we replace the nonce, which is numbers used only once, with unique block identity tokens, UBT. And as a result, we have a new block structure and working with a new for a new consensus algorithm. And this is the very simplistic consensus algorithm, where our objective is to validate the block and using cryptographic mechanisms. Okay, so and again, this is more applicable for private blockchain, not for public blockchain, and long way to go. Rather, it needs a lot more work in this respect to when we are putting it in a completely public blockchain. But private blockchain has a lot of application, and that is what we advocate to use, because rather our philosophy is using of public blockchain should not be always explored, rather discouraged, because blockchains are public blockchains are quite energy hungry. We may not need that in most of the time. So when you compare in terms of power computation demand, okay, blockchain in a public blockchain, let's say consuming this much power, okay, and in that respect, our public blockchain we're running in a Raspberry Pi computes uses only 5 watt of power. So we did a comparison proof of work in with a serious power usage is taking minutes of time, and hours with very minimal power usage is taking seconds of time. So it's we have verified this design, and we claim this easily we can say 200x faster. Now, what did we do? We further went to basics. We thought, okay, why don't we even take out the cryptographic part? We take just put POPs everywhere. So different blockchain nodes have different POPs, that is physical unclonable functions, and they will do the authentication and so on. That is what we did, and we call this chain as POP chain. And so again, we're going back to the basic. We have client nodes with POP, we have trusted nodes with POP, we have and these trusted nodes in decentralized fashion authenticating the client nodes. That's the idea. Okay, and as a result, we came up with a new blockchain. We called it POP chain, and a new consensus algorithm we call as a proof of POP-enabled authentication of POP. So essentially, that means client nodes with POP and trusted nodes with POP, they are authenticating each other. Okay, and as a result, we have a very fast consensus algorithm. So we went back and we changed again the blockchain structure. The block structure has now more information, that is the POP unique identifier and so on. And as a result, we have a foolproof solution. And this is the enrollment process where POPs are working, POPs are generating challenge response pair, and then use sending back and forth for verification purposes. And then when a new block wants to be validated or a new client device wants to be validated, we follow the protocol of POP and then validate the new when there is a good match of both side POPs. We verified this work, okay, which is running 1000x faster than the proof of work, okay. It's very fast and very, very robust security because POPs are there. We developed another blockchain. We call it multi-chain approach, where our chain structure is much more compact, and the chain can store a lot more data. So this is far beyond any blockchain that we can imagine. Okay, and, like not just a Bitcoin blockchain, or we have a proof authentication based blockchain, but something coming now more robust as a Tangle Hashgraph. We have done far beyond that. We call this now a next generation blockchain, where it will be multi-chain as well as a lot of storage capability. So the blockchain, okay, we are a dynamic block list we have, and that we are making compact list all the time, and dynamically block chain is being optimized for storage purposes. And we did a different block structure to take into that account. So we are keeping track of from the Genesis block, how far a block is there and how we can optimize we are able to do. Okay, this is an excellent result we have. That is doing in some milliseconds, okay, authentication and so on. Smart grid solution, another security solution where it has a lot of importance because it's controlling the smart grid, and it can definitely use blockchain in various ways, and people are trying. Okay, that is at the energy grid level to microgrid level, all these places blockchain can be explored. And this is a very interesting work that I did in collaboration with NIT Rourkela, where we are combining as eternal thing, we are combining security and energy harvesting. So it's excellent result we have. We are doing next generation of it, and we are what you can say going for additional security features. So we know now data is very important. Okay, we need a lot of data, and we have discussed all these slides so far. I showed many things that emphasizes the security of the device, the security of the system, which is, as now we know, are much more life critical. Okay, much more serious consequences, direct consequences compared to data security. But data is very important. Data is important because data makes things intelligent or smart, that we call. We develop models based on it, and those machine learning models essentially giving us the smartness that we are looking for. So centralized data that is in the IoT cloud, okay, in the traditional sense, has been doing a lot of things for us, but there is now a lot of advocacy to get away from the centralized fashion, rather having a distribution, decentralized way of data is what getting attention. With that, we gave the concept of edge data center. How do you distribute workload between them and so on, among them and so on? That is the idea here. And we gave a solution that how, when we have a lot of different edge data centers, how do you load share between them, how to provide security among them, all these things we have developed. And this is doing fantastic job. That is, we have successfully reduced power up to 30% in those mechanisms while providing security. And data security, that is, we know day-to-day life we face this situation that cannot be overemphasized. And at a basic, as a basic mechanism, we protect our hard drives with hardware-based encryption is a basic step forward. Okay, and software everybody does using, for example, BitLocker kind of mechanism. Okay, and TrueCrypt, VeraCrypt, all these software solutions are there. Okay, and because data needs to be protected. Now, far beyond the data that can protect in the hard drive, which is a non-volatile storage, long-term storage, but in the embedded system, the main memory, the DRAM kind of mechanism, then cache those, how we can protect those. So we have some idea that we did, that is how to have main memory protection using on-the-fly encryption that does a very good job of protecting. At the same time, doesn't consume a lot more power. So that work we did, where we are protecting not just a hard drive here, which is a rather easier problem. Okay, this is a difficult problem because we are doing on-the-fly protection, at the same time not doing any override. And we have been discussing that is how, what is that side channel attack can cause a problem. So where we are studying the profile of the hardware, and then we are doing solutions, okay, that is giving us the keys and so on, okay, which is essentially breaking the hardware encryption without breaking theoretically or the brute force fashions, okay, but by doing power analysis and so on. And we can basically defeat those side channel attack mechanisms by using different mechanisms here we have, where security, that those kind of side channel attack hackers cannot get the power profile, cannot guess. So this I was doing like as a part of my PhD, and some other collaborators and so on also have worked on this. And this is the slide that tells how we can basically confuse people what should be the green color here as the actual power profile with a different power profile, so that the guess cannot be easily obtained. So this is the, I always show this slide, that is wherever, whether it's edge or end or cloud, we'll have to have always trade-off of the security and intelligence. Okay, and when I'm talking about security by design, okay, I have to worry about having the security, but without compromising additional things that we are also putting, specifically intelligence. Okay, intelligence comes from data, but the model at the end runs on the hardware at different nodes, okay, where depending on whether it's end, edge, or cloud. So NFC, I was telling, is a very important component, and it needs to be protected. And this is an idea that we developed, where we are saying that is with biometric kind of security, fingerprint in this specific case, how we can secure the NFC. And this is RFID security. RFID is a significant component, small component, but a significant component of the CPS, and we can protect it in many ways. Okay, and for example, like a blocker tag is creating a safe zone, okay, so that RFID reader cannot read it easily. So that's a security method. Now, yesterday we are showing this slide, that is machine learning mechanisms are important because using machine learning, we are retrieving information from the data, and that machine learning then helping us to make certain decisions. Okay, healthcare is critical, so as we can do in, for example, environmental monitoring we do, or agriculture we do, and or like energy related, so machine learning models will come handy. And so that's why what needs to be ensured is the data that we get are good data, so that models are good, that is built on the data. And this is a very interesting slide, that what I tell, that is how critical is data, and how model can be really problematic than a solution unless we are careful. Okay, so for example, this is a slide, I'm in slide number 134, and what I show here, that is let's say we have a machine learning model, how a model will differentiate between the actual thing and a dummy thing. Okay, so those are serious things, so serious problems, and if data is not good, then we may get into those kind of problems. Okay, and the right side is much more serious situation, where we are talking about in comparison to the left side is fake data, right side is fake device. So let us say we are doing a serious what you can say pacemaker kind of surgery to put a pacemaker in somebody's body, and the pacemaker is a bad hardware, fake hardware, or a compromised hardware which is essentially like refurbished and so on. Okay, those are serious problems. So as you can see now, direct fine what you can say physical consequences can be there. Then in the bottom, I have a very interesting slide there in the bottom, that is we are using autonomous cars. Okay, and let's say brake system, I have a bad hardware that I bought from market, which is not a good market. Okay, and as a result, brakes of my car is compromised. Okay, that can have serious problems. So solution point of view, watermarking has been explored, and I have done a lot of work. So that was my left side was my master's thesis, essentially in like late 90s. Okay, when I was a student in Indian Institute of Science in Bangalore. And then right side are solutions we came up with for hardware in last 5-10 years. And that's why I wrote a very interesting article, okay, about watermarking, that because I'm one person who has worked starting from signal watermarking till hardware watermarking, so the complete picture. So in the hardware domain, okay, if you see this slide number 134, if you see that, then the problems are similar in the sense fake versus real. Okay, real data versus fake data, similar real hardware versus fake hardware, and all these have serious situations, implications rather, I would say, in the CPS. Now, this hardware I developed long time ago. Okay, that is that has got. So, in fact, this is the first watermarking chip which was low power watermarking. Okay, I developed that when I was doing my PhD, and this has a power consumption of 0.3 milliwatt. Those days we used 0.35 micron technology and did the complete design, okay, with 1.4 million transistors. And this hardware is able to do watermarking, and it was DVD compliant as far as I remember, and resolution point of view, and consumes very minimum 0.3 milliwatt power. And that work has basically motivated a lot of people. This is one example where in Austria, they use those ideas to develop a camera, okay, which is doing authentication and so on. And this is the same, my watermarking work has what you can say motivated people to do sensor level. That means in the camera, you have the CMOS sensor, current generation camera CMOS, than the previous generation, which are CCD based, okay, and how they came up with an idea to do secure sensors. So with this, we covered the security full spectrum of security of CPS, and we have different, like security, as I said, is a bigger umbrella with security, privacy, IP protection, all these, they are related, but they are not same. And security of data, device, all these things are important. And right now AI, which is coming from the data, but AI before model, after model can have security problems that we need to deal with. And both software hardware based attacks and corresponding solutions can be there, and hardware based attacks are much more difficult to what you can say diagnose. Okay, and existing solutions have a lot of overhead. We need to work on that, and hardware assisted security is a very good paradigm, okay, which is subset of secure by design or security by design. So privacy and security by design have essentially originated so that people go to the basics of the design phase and avoid retrofitting. That's the big idea. And information system, all these have to have protection and privacy awareness as well as security solution. And bottom line is sustainable smart cities needs sustainable IoT. That's the big picture. Okay, and with this technical part are over for this presentation, and one or two slides I just tell to bring your attention. Okay, I know all of you are, this is a faculty development program, all of you are faculties, and I do encourage, that is, I go to India almost 2 times in a year, right? I go, my parents are there in Bhubaneswar, of course, and what I tell to the professionals that I meet, I go to various states, like I go to in India, I have collaboration not just in Odisha with Rajasthan. Then last summer I visited Delhi and Kanpur, and NIT Jaipur I have been going. Triple IT Naraipur I was there last year. A lot of works I'm doing in collaboration. So I always tell that it's a good, very good rather idea to be part of the community. Okay, so IEEE is world's largest professional society with like 500 million members in 160 countries. So we need to be a part of that community to remain in the profession so that we are networked. Okay, we are all researchers, we are all engineers. So I definitely recommend all of you to join IEEE, and this is a consumer electronic society which is now called Consumer Technology Society. I just helped around let us say 40 to 60 people in Odisha, various parts of Odisha, to form a Odisha Consumer Technology Odisha chapter. I definitely recommend all of you to be members, and Consumer Technology Society is one of the society with the least amount of membership fee. Okay, so you pay the IEEE membership fee plus Consumer Technology Society fee, and you are a member and you are staying connected with the people. That is the key idea. And this magazine that I am the editor, this is a magazine, you are welcome to submit. Okay, and this magazine, even though we spend a lot of money in a year, we spent easy $150,000 to publish magazine. Okay, that comes to you, to your doorstep every month, alternate month. Okay, printed nice color. Okay, so the membership you are paying, that essentially given back to you with the hell in the form of magazine. You're getting every alternate month a magazine, nice color printed. So it's not really costing you anything. It's like essentially buying the magazine. Okay, with that cost of the membership. Anyway, so I definitely recommend you will be associated with a lot of people, including me as a director, and you will get a lot of advantage. And the transaction also is there. Society also has a transaction. Okay, and again, I'm on the editorial board. I've been helping both the magazine. I'm the editor-in-chief, and transaction I'm in the editorial board. So all these both are very high profile. As you can see, magazine impact factor is 4.016. Okay, and journal has close to 3. I don't remember exactly number now. But anyhow, so you can be part of all these. Okay, and I definitely invite. And this is another thing that I bring to attention, that is to like a lot of people, right? They want to travel to US or other countries as a part of their professional activities. Okay, to attend the conference, for example. But what I did as my effort to give back to India. Okay, that is India. A lot of people are here, but I always thought how to give back to India. So this is one effort that I started and has been running in India. And last year it was hosted by NIT Rourkela, and this year BIT Chennai is doing. They are a Institute of Eminence, BIT Chennai, and they are hosting it, okay, in December. And next year it will be in NIT Jaipur. So I definitely recommend. This is a pure IEEE conference. Everything is managed in IEEE US essentially. That means in the New Jersey office, everything takes care of budget, everything. We just because I wanted to give back something to India, so this is we're just doing location as India, everything managed in US. But this what is the important feature of this? That is, you are in India attending a conference, okay, with a lot of people going from various part of the world as well as in India. And last year when it was in NIT Raurkela, okay, like all NIT people were there, some IITs and all NIT people are there. So that's a big networking effort for you. I definitely encourage all of you to be part of it. Okay. So with this, I conclude the talk, and then I'll be very happy to take up your questions that you may have in any technical as well as non-technical matters. Thank you.
Good evening, sir.
Good evening.
So, am I audible?
Yes, yes. I opened the chat. If anybody has any questions, we can. Okay. Yeah. So go ahead with any questions that you may have.
Yes, sir. So, as we started with the presentation, sir, you had mentioned that pacemaker is also getting hacked. So that also needs to be secured. So if it's getting hacked, so then you had discussed regarding PUF, sir.
POP, sorry. Yeah.
Yes, sir. So the first thing is so we don't store keys. So I would like to know. So then, what is the mechanism behind PUF, sir? So what is so it's a numeric data, or so what kind of data goes into the encryption using PUF?
Very good question. So using POP, we are avoiding encryption. You can simplistically think. Okay. So first, briefly saying what is a POP. It is a hardware security primitive, we call it. That means it's a hardware that has capability to have some unique numbers that will come out of the hardware. So those numbers will be used for authentication purposes. Okay. For example, if you comprehend the situation like this, let us say you have a lock, okay, and a specific key can only open that lock, not any other key. Okay, so POP is essentially generating as a output certain numbers, okay, and those numbers are coming from that specific POP. If any other POP, they won't give them those numbers. Okay, so so you are not storing that number anywhere. Okay, you are generating that number whenever needed by executing the POP. Okay, so you have that sequence of number coming by running the POP, and that is being used as security mechanism. Okay, and we are avoiding cryptography, but if you want to do cryptography based on the POP, you can do as well. Okay, so then you have to build the rest of the cryptography processes. Okay, and then you can do your POP based cryptography as well. Okay, very good question. And this is so basically the point here is to have less energy overhead to provide security. So that's why this is a very interesting solution. Okay, that is working, and that's why it's getting like blockchain is getting a lot of attention. Okay, and blockchain is getting attention from the software side people, from the hardware side people. POP is getting a lot of attention as a result.
So what I get right now is PUF is something which we will be executing every time we require to use it for security purpose.
Yes, yes, very good. That is simplistic understanding. Okay, and what you can use, so it's a hardware entity. Okay, so then your obvious question, what are the hardware entities that will give me PUF, right?
Yes,
so for example,
I was just going for that itself.
Exactly. So we have done variety of POPs we have done with I was showing you one eternal thing example. I told that's excellent design we did, and NIT Rourkela, I helped them. That's a POP which has a energy harvester built in. Okay, and we use ring oscillators as a POP circuit. Okay, but to give an example, you can use memory modules as POP. Okay, and ring oscillator, then like arbiter circuit, a lot of varieties. Okay, then for example, SRAM you can use in a specific way as a POP. So it's a hardware. What is the key idea there? That is those hardware, it's at the circuit level, right? You have transistors and so on. Okay, so a specific transistor and other combinations is giving you those one and zeros. Okay, and so that's why a lot of topologies can be explored to be used as POP. Okay, there are variety of topology there. And if you read our POP chain paper in archive version, we have a complete discussion. Okay, you go to my website, archive version has a complete discussion of variety of POPs.
Yes, sir. So
Okay,
so I'll just extend another
sure.
part to the question.
Sure.
So going back to the pacemaker from where I started, sir. So can
Sure.
puff be again used in those kind of medical? So whenever we are getting medical data, so we are just like receiving or medical data based sensors where we are using and collecting data. So can
Right.
puff be also used in those conditions?
Yes, that is the whole point here. Okay, encryption cannot be used because
Yes, sir.
those medical devices do not have the horsepower or the computation capabilities. Okay,
Mm.
blockchain is not easy to use. We have, in fact, we ourselves have come up with the approach where blockchain can go to those devices. Okay, but they are still very difficult. So in this situation, POF is a excellent solution. But I also know the problems that it can have if we have put a POF. At least this is so far the best solution. Okay, that is put a POP and that POP is executed and used for security validations.
Okay, sir. Thank you, sir.
Sure, thank you. Any other questions? Okay, so if you have any other question, please feel free to ask me right now, or you can put in chat window, or please feel free to email me if you have any questions. I'll be more than happy to. As you now know, I help a lot of people in various different states, and of course across the globe. I work with a lot of people in Europe and the US and so on. So I'll be more than happy to help you on any questions or any research help that you need.
There's a question, sir.
Yeah, so solution to double spending issue in blockchain. Okay, so there are solutions. Okay, that is because I was just mentioning to Swati, there are two things people are globally working. One is blockchain and second is POP. And blockchain predominantly is software kind of people are working. Okay, and even though originally when it came, it was not meant for that purpose. The application that you're exploring. But people are working a lot of solutions to various secret problems are there. Okay, so you can definitely, I can share with you different articles that has solutions. Okay, and then POP, I was mentioning, hardware people predominantly worked, okay, on that, have been working, and a lot of solutions are there, and both have long way to go. Okay, both blockchain and POP, and particularly we just discussed that POP can be used, blockchain can be used, but they are not straightforward. A lot of solutions out there, and what is interesting is it has to standardization. Okay, for example, in medical things, okay, or any other domain we take. Okay, standardization is very important. Okay, so that people understand those technologies and use specific things that is understood by everybody, let's say medical community across the globe. Okay, and then energy community across the globe. So those are more direction that I think that is standardization of technologies that is used in CPS has to be there more. Okay. Somebody asked, except Hyperledger and Ethereum, is there any open platform used for blockchain? Answer is yes. Okay, that is, and I leave those actually to students. What I always tell my student that is depending on what you like use. For example, like Ethereum is a smart contract. Then another smart contract is there, Nero. Okay, and when I search in Google, okay, I find always a lot of Hyperledger is from IBM. Okay, so always a lot of solutions. Okay, so definitely are there. Okay, and in fact you go to IEEE Explore. Okay, I rather a person who tells, okay, you choose a blockchain that has a minimal energy requirement. Okay, that means you first decide whether really I need a blockchain, okay, or not. Okay, don't go to blockchain just because people are saying that will work. Okay, you may not need a blockchain. So in fact in the IEEE Explore recently, we have an article that addresses when do we need a blockchain. That I'll definitely bring that to your attention. Read those. That Blockchain, the answer is, I tell very simplistically, you need a public blockchain only when you have untrusted parties. If you do not have complete untrusted parties, do not use a public blockchain, because that is unnecessarily energy overhead for you. Okay, and then it has other limitations like storage and so on. Okay, so first make up your mind whether it is needed or not needed. If not needed, do not use. Okay, then private blockchain can have much more advantages if practice are not necessarily all are untrusted. Okay, and a lot of implementations are there. So the question was, in addition to Hyperledger, Ethereum, is there anything else? Answer is yes. Okay, a lot of them are there. You can search in Google. GitHub always has a lot of resource, and I can also share if you send me an email. Thank you.